So there we go, should be going. All right, so this is the 13th session in our ongoing GPU workshop series. And like I said, today we're going to talk about using the using the GPUs in a Dask context. Mostly in this, we'll talk about using it with CuPy. But if there's time at the end, we'll also do a little bit of introduction for cuDF, which will play into next week's session, or in 2 weeks, the session on machine learning. So here are just some instructions for obtaining the notebook. Hopefully you've had a chance to do that and pull the latest updates to the GitHub repo. And then the usual points about etiquette. Please just keep yourself muted and turn off the video during the session. If you have any questions, feel free to put them in the chat and we can address them, or you can raise your hand or unmute or ask questions at the end. And of course, we expect you all to follow the code of conduct and feel free to reach out to us after the fact on the Slack. So I just wanted to start off with doing a bit of a refresher from 2 weeks ago when Brett talked about the CuPy package and how that provides a GPU drop-in replacement for a lot of NumPy functionality in Python. So this allows us to do operations on data arrays in a GPU-enabled context. And one thing we're going to monitor a little bit more in this session is the GPU resource utilization. So you'll notice on the right side of my screen here, I've got these two panels up in my Jupyter Lab interface. I've got a GPU utilization dashboard and a GPU memory dashboard. And this one in particular is going to be pretty useful. And these are accessible from NCAR's Jupyter Hub. On the left here, there's this third icon. And if you hover over it, it says GPU dashboards. If I click it, I have all these various options, and I'm just looking at the utilization and memory here. But the other ones can be of use as well. So keep an eye on these things as we do GPU operations. All right, so I'm just going to run through some commands and we'll sort of review a little bit of what Brett talked about last week. So I'm going to go ahead and just create some data arrays on the CPU and on the GPU to do some comparisons. So we'll import NumPy and we'll import CuPy here. We'll have both libraries available to us. And then just do a very simple creating of a Gaussian array on the CPU with NumPy. It's going to be a 10K by 10K array of random numbers. So fairly sizable. So Ben, I see your question. Is there also a CPU dashboard? There is. In fact, if you click on machine resources here on the GPU dashboards, it will talk a little bit. It'll show you a little bit of information about the sort of the CPU usage, even though that's not necessarily the intention. You just click on it. You see CPU, memory, disk I/O, and network, and this will stream as it samples. So that's a nice way to get that information. And then of course, there's always the memory counter on the bottom for just memory utilization. Okay, so we've created this NumPy array on the node, and we've used 763 megabytes of memory. So then creating the same array on the GPU, we can construct it here. And notice it's the same drop-in command. All we're doing is we're changing NP to CP to use CuPy instead. So we'll run this, and you'll notice I'm using the n bytes attribute here, and then just dividing by 1024 squared to convert to megabytes. And we can see it's the same exact size. Now these aren't the same arrays, but they are the same size data structures. You notice here that on my GPU memory dashboard, one of the two GPUs that I've allocated here on this in this job has reflected that memory usage. So then obviously, the thing we care about when we're using a GPU is the speed, right? So we can just do a simple timing of running a mean on both of these arrays. So if I do that on the CPU, it's still blazing fast. This isn't a computation that I necessarily need to leverage GPUs for. We've got the mean of this, random number array. It's close to 0, which is what we'd expect. And this only took 65.8 milliseconds, so very fast. Now, if we run the same thing on our GPU array, we'll actually see that it's quite a bit slower. We get a different value of a mean because, again, it's a different random array. But this, this harks back to something that I think we talked about 2 weeks ago. That a lot of times with CuPy, the first time you run an instruction on a different data structure, it's going to take longer. There's a bit of overhead. And what CuPy is doing there is it's actually constructing on the fly a kernel that's specifically sized to the data structure you care about. So once it has constructed that and we run it again, Now we can see it's a lot faster, and in fact, a lot faster than when I run on the CPU. And you'll notice if you're paying attention to the GPU utilization dashboard, for a very brief instant, we saw a good bit of SM instructions going on one of the two GPUs. And then, of course, we can think about checking the GPU just for correctness. It's always good to do. Not necessarily that we don't trust the GPUs, but just if you have a more complicated workflow, you always want to make sure that the changes you've made to offload to the GPU haven't affected your answer. So we can copy our CPU array to the GPU here. You notice that I'm now using even a bit more GPU memory. And then I can do something like take the mean, which I'll do here. You can see we got some GPU utilization. And if we compare this to the value that we got up here, we can see to a sufficient number of digits, it's the same. Obviously, we're working on floats, so you would expect maybe small differences there. So we've done some basic operations here. Now this sort of brings into the monitoring aspect and thinking about memory usage, because that's going to be important when we think about using this with Dask and scaling up with Dask. So CuPy provides an interface to query the memory usage by the data structures that CuPy has created, and it also allows us to query what's called CuPy's memory pool. So when you allocate an object using CuPy on the GPU, it basically, it allocates that space in video RAM, but it also expands the memory pool that CuPy is aware of. And even if you delete that object, if you deallocate it after, the memory pool is going to hold on to that space in memory so that if you do subsequent operations, they should be faster. It shouldn't have to do that overhead again. This is generally a good thing, generally something that is, helps our solution be more performant, but it's still a good thing to be aware of and monitor. So CuPy provides this interface. You can do get default memory pool. We can just assign it to a variable. So we'll do that here. And then I define this little function. So this little procedure. So basically, I'm just doing two prints. And I'm printing out the use memory, which I'm doing from mempool use bytes and then converting to megabytes. And then the total pool, which is, again, the size of the pool of memory on the GPU. So we'll define that and then we'll run it. And we can see that because we've copied those two 700 and some megabyte arrays onto the GPU, created or copied, we're using double that space in the available memory, and the memory pool has expanded to fit those two data structures. But one thing that we probably want to do at certain times is delete those data structures and clean up. This in Python doesn't immediately deallocate necessarily. So for NumPy structures, it will. But you're not necessarily going to, and for CuPy, in fact. But for certain Python structures, it's not necessarily going to do that. It's just going to, at the very least, mark it for the garbage collection that Python does regularly. And it deallocates and frees that space in the memory pool on the GPU. So we'll run that. And then we can run this again. And now you'll see here that the use memory reports as 0 on the GPU. So it did get deleted. That's good, that our GPU array and our GPU copy. But the total memory pool is still the same size. So it's still holding on to those addresses in memory, in GPU memory. And that's reflected in this dashboard. So that's something to note. If you use this dashboard for GPU memory, I think it's really powerful. And I think hopefully you'll see that by the time we're done. But just be aware that if you delete an array, it's not necessarily going to reflect here in the GPU memory because we have that total pool, that memory pool that's being capped by CuPy. However, we can also explicitly release the GPU memory from CuPy's pool, from its memory pool. And I would say generally you don't have to do this, but this step can be useful if you're utilizing, say, other GPU libraries in your workflow, and you want to make sure that your usage goes down to whatever it would be after deleting your CuPy arrays, to make sure that that space is available for, say, other allocations. So we can run mempool free all blocks here. And if we run that, now you'll notice this has dropped down very low. It's not to 0 because there's still a CUDA compute context that CuPy is running on that GPU. But it's essentially, it's for all intents and purposes 0 and still able to do work. And if we run our method here one more time, we can see that we have now a total pool size of 0 megabytes. So we've done all the cleanup that we can really do. So these are just some useful tools. There is also a pinned bit of memory that that CuPy tracks on the node to allow for data transfers to and from the GPU, and that can be deallocated as well. But I just wanted to show the GPU part of it right now, because generally you're going to be more constrained by GPU memory than by node memory. Okay, so now that we've looked at that, let's track the performance and the memory usage for something a little bit bigger. And I didn't want to make people have to download a big file and provide access to that and all that. So I've written this kind of silly function that uses some NumPy methods to produce a facsimile temperature data set. And it's flexible. You can specify dimensions here, so nx and y, and then a time dimension. Feel free, if you're going to explore this notebook later on, to play with this array size, but just be aware of the memory footprint as you use this, because it can get pretty big. So we'll define this, and then I'm going to just kick this off and running on an input of 4000 nx, 2000 ny, and 140 nt. This will take just a moment to run. Now, notice I'm using the NumPy functions here. So this is generating this array on the this three-dimensional array on the node, not on the GPU. There we go, it's done. And we can see that the size of this is 8.34 gigabytes. So it's pretty big. And what I've essentially done here is I've used these to produce a data set that, if you squint, it kind of looks something like a surface temperatures data set, maybe on an aquaplanet, or at least one that doesn't have any weather. So if I import PyPlot from Matplotlib, and then I just do a filled contour, I'm going to take the transpose here just to have the indices in the direction that I want, so that nx is in the x direction. There we go. We can see it's warmer at the equator and it's colder at the poles. So at least it kind of feels like a planet. And what I'm doing here, I don't have a bar, but I'm generating temperature values that are in units of Kelvin. So you see 287, 289 is sort of the range that I'm playing with here. So you can look at the details of what I'm doing in there in your own time. Basically, we've produced a data set that we can use. So now what I'm going to do is I'm going to copy this bigger data set into the GPU, and we'll see what happens with the memory usage in the memory pool. So I'll run my method, and then I'll copy as an array to CuPy to the GPU, and I'll store that as TG for temperature on the GPU, and then we can run our function again. So there we go. We have nothing here. You'll notice it's already allocated the space on the GPU for the structure. And there we go. I had to do a bit more work to make it happen this time, but now we can see that we've got that space used up and also allocated as part of the pool on our GPU. Now, obviously, we've got a bigger data set, and it might be interesting to do some computations on that, just to show that hopefully the GPU is doing something useful for us. So let's compare the performance of a relatively simple operation. Here I'm going to subtract 273.15 to convert to Celsius across the entire array. And then I'll take the mean on the second index dimension, third dimension, so the time dimension, and we'll flatten it basically so that we get the mean temperature across all times at each grid point. And you notice first we do this on the CPU and we time it, and then we'll do it on the GPU and time it and look at our memory statistics. So I'm going to run this first on the CPU, and we'll see what we get. Didn't take too long. NumPy is still very efficient C code, so 3.51 seconds. It's not too bad. And it's interesting. You'll notice that this is a bit touchy of a marker. I'm sure the GPU is doing something there, but it's not actually doing any computation on our NumPy array. So that's sort of just some, like if you had like a Geiger counter pointed at the ambient environment, you'd get you'd get some noise, but it doesn't mean you're right next to a nuclear reactor. Now here, if we run the GPU version, it's much faster. This is 431 now milliseconds. But something to note is that the use memory at the end is what we expect, but the total pool is actually about double that. And that goes to show that there's some intermediate data structures that had to be created to do this. And when those intermediate structures were there, this sort of gives us an indication of what our high watermark is for this operation on the GPU. And you can see that that was more around like 17 gigabytes. So if we wanted to operate on a data structure that was twice this size on the GPU, we'd already be looking at exhausting our GPU's video memory. So that's not an ideal situation to be in. And it's unfortunate because we've seen such a big speed up. And I wonder if we run this again. See, now it's even faster because we've got that GPU kernel that's been created by CuPy. So at this point, we've got a very significant speed up. Now, if I were to run the CPU version, again, the timing would be pretty similar because it's not doing anything like that. So this speaks to the fact that we need some way to scale up if we want to look at bigger data sets. And that's where Dask comes in. So I'm just going to go ahead and do some cleanup again. We'll delete our arrays. And then we'll use free all blocks to make this ugly yellow bar go away. And we'll look at our stats and our function as well. So there we go. We've basically cleaned up our GPU, and now we have a total pool size of 0 in addition to a used amount of 0. And again, if you're just using CuPy, really cleaning up the pool isn't necessary. And in fact, it might hit your performance a tiny bit because generally that memory pool exists to keep things performant. But we're just going to do this to sort of be able to see what's happening to the memory usage very clearly. All right, so I'm going to do a bit of introduction on Dask just generally. I'm guessing most of the audience here is familiar with Dask since it's very popular at NCAR, but I just want to make sure everybody's on the same page. So Dask is a popular Python library for parallelizing computations across multiple workers. One of the really nice things about Dask is it's incredibly easy to scale the code from problem sizes that could fit on like an underpowered small dual core laptop to something that can span an entire cluster like Casper if you were able to access all of the resources at once. And it's able to do that without too much in the way of code changes. Since it's part of the Python ecosystem, Dask is also easy to install using Conda. It leverages high-level collections like NumPy arrays and pandas data frames, and I think that's one of the reasons that Dask has really become so popular is because it very easily extends the existing PyData ecosystem. And Dask can schedule workers itself, or it can leverage components to submit jobs to schedulers like PBS and Slurm, so you can get access to resources that aren't necessarily on the same node you're on. And relevant to our session, of course, Dask workers can use GPUs. And sort of the take-home message from the Dask tutorial that I like is that Dask allows you to scale up from problem sizes that fit in node, or in our case in GPU memory, to ones that can fit on disk. And parallel file systems are very big, quotas are very big. So this really allows us to expand what we're doing by a lot. So just to dig in a bit more on the fundamentals and how the GPU is supported and how it fits in. So, Dask, as I mentioned, operates on either a high-level collection of data like an array or a series or a data frame, or in fact, it can operate on a low-level collection of more arbitrary code. You could just define, say, a function, and then decorate it to run in Dask in a delayed way. So basically, you define the function and then tell it to run in parallel, or asynchronously using what's called futures for either way for parallel execution. But in this tutorial, and that's really powerful, people will use that, especially I think it's used pretty commonly in like setting up machine learning workflows. But in this tutorial, we're going to focus really on the high-level data structures, in particular mostly CuPy. But here's a summary of how things look. So we've got our 3 high-level collections. We've got the, well, 3 of them. We've got the array, the series, and the data frame, all the Dask components, the Dask variants of them. But underlying those, you're going to typically have a CPU object, which would be either a NumPy array or a pandas series or data frame. If we move to the GPU, we're just switching out what's underlying the Dask structure. So on a GPU, we would have a Dask array that's made up of a bunch of CuPy arrays, or a series or a data frame that's made up of a bunch of cuDF series or data frames. And just a note about compatibility with GPUs. So as Brett mentioned 2 weeks ago, CuPy is cross-platform between NVIDIA and AMD. It supports CUDA and ROCm. Whereas cuDF is part of NVIDIA's Rapids package, or suite of packages, I guess. And it's really, the development's driven by NVIDIA. So at least at this time, it's pretty locked into NVIDIA hardware. I'm not really aware of a data frame solution on AMD GPUs, but if anybody else is, feel free to put it in the chat and share. Okay, so that's sort of our high-level collections that we care about in this session. I sort of hinted at this earlier, but one thing to note about Dask is that it uses, for the most part, it uses lazy evaluation. And what that means is that you tell Dask what you want the workers to do on your data collection. But then Dask is going to wait until you explicitly start the computation using, say, .compute, for example. There's a couple of other methods to kick it off as well. But .compute would sort of be the most simple way to get it going. And what you do is you're going to run that on what you've defined and is called a task graph, which is just a sequence of operations that you want to run on your collection of data to get what is typically a reduced output. And then you map that out and you submit it to a scheduler. Now, one thing to note is that worker memory, either on the CPU or on the GPU, is not consumed until you actually begin executing the task graph. I mean, obviously, creating a task graph uses a tiny bit of storage, but we're talking probably like kilobytes there. And we're not actually doing anything with data until we submit it to a scheduler. Now, I like this diagram, which is why I put it here. This is from the Dask website. And this shows kind of a summary of the collections. I didn't mention Dask bags. This is sort of their high-level collection for mutable data things like lists in Python. So, you know, it has more of a different focus, I would say, than the more data science-oriented ones like arrays and data frames. But it is, you know, it's generalizable, which is nice. So we have our collection, we assign it a task graph, which again, these are just like, this is a task that's running in parallel on, you know, different workers, and then you reduce it down and you reduce it down, and eventually through, as you flow from left to right, you get to your answer, your output that you want. And this then gets sent to a scheduler to execute. So the simplest way would be to send it to a single machine scheduler. This comes with Dask by itself. But if you add on the distributed package to Dask, now you have access to more complex scheduler. And when I say scheduler in this case, I mean a Dask scheduler, which executes Dask's task graphs. I don't necessarily mean like a batch scheduler like PBS or Slurm, though they are options in distributed to use as schedulers. So this is fundamentally what I've shown here is all relevant to using Dask on CPUs. The only thing that's different on a GPU is sort of the high-level collections that you are using, and maybe the scheduler you might use could be slightly different and customized, and we'll show that. But there's really nothing about the workflow in terms of the big picture that's different when you use GPUs. So when might you use Dask with GPUs? You know, I like to mention that while Dask is easy to use, you know, even the simplest of parallel computing approaches are trickier to get right than running sequentially. It's pretty much almost a universal axiom, I think. So, you know, there's more to think about. So here are some scenarios where I think that using Dask with GPUs is powerful and it's compelling. So one is obviously, this is the base case. If you're lucky enough to have many GPU resources and there's very low contention on the system that you're on, and you can be bursty, which is, you know, Dask's very good at scaling from a couple of workers to a ton of workers. It's like if you have a whole DGX cluster to yourself, you're in the NVIDIA lab or whatever, and a blessed user, then go for it. You know, you might as well leverage those resources. But, you know, if you're not so lucky, there's still use cases that make sense. So if your workflow just benefits very, you know, tremendously from using GPU acceleration, maybe you're going from, you know, many hours on the CPU to like 10 minutes running on the GPU. You know, that could be really, that could be a really good reason, especially, you know, if your data set is too big to run on a single GPU and you need to use Dask to spread it across multiple devices. You might have to wait a little bit for your batch scheduler to assign you those GPUs, but that's probably going to be more than offset by that performance speed up you see from using the GPUs. Another case would be if a small segment of your analysis workflow can benefit from on-demand access to GPUs. This is like, well, most of your script is happy to use CPUs, but there's like one little kernel of computation that can be sped up greatly. You don't want to have to ask for a GPU that whole time, but maybe you can use Dask to ask for a GPU for just a little portion of that. And because you have all your data loaded into memory already, it's very easy to then like move it to a GPU or multiple GPUs and not have to do multiple data loads into memory for different components of a script if you split it up. And then finally, I don't really talk too much about this in this session, but I think we'll probably talk about it when derecho arrives. If you're running a large application that's MPI enabled and you're running multiple cycles of it in a single job, you may wish to do data analysis or data, say, pre or post processing between cycles. And you could spin up a script and use Dask MPI to basically use that MPI communicator you have to spawn Dask workers. And that could be useful with a CPU context as well. But if you have a model that already is asked for, like, knows with 4 GPUs on them, it could be really compelling to use those GPUs for that processing. So with that background out of the way, let's do a little bit of demonstration. So here I'm going to use what NVIDIA provides this as part of Rapids. They provide this Dask CUDA package. And I guess I should show here, these are some notable packages that we'll talk about. So there's the base Dask package, there's distributed, there's Dask Job Queue, which provides access to our batch schedulers, Dask CUDA, which provides access to this, and also a CUDA worker instance, and then Dask MPI, which I talked about. So why would we want to use Dask CUDA? So Dask CUDA provides us access to this special cluster type. A local CUDA cluster isn't required to use CuPy and cuDF collections with Dask. You could do it with one of the standard Dask clusters. But what it does is it eases the pinning of local GPUs to specific workers. So if you have multiple GPUs in your visible devices, you want to make sure that each worker is talking to, or you have like certain workers talking to each one. And a one-to-one is fairly common. It's kind of the simple case. The other thing it does is it can provide high-speed worker communication via the UCX library. Now, I'm not going to use UCX in this talk because UCX has to be compiled for your system, and you have to do some customization in your environment to make that work. So I'm going to avoid that here in the case of simplicity, but I have this link in the notebook, and I recommend if you want to maximize your performance for like those data transfers that you have to do to say get your result back or sort of spin up the workers, using UCX can really speed that up. And it can also allow you to utilize things like NVLink connecting your GPUs. All right, so first we're going to go ahead and start our cluster. You'll notice I'm importing the Dask array as DA. I'm importing a client object from Dask distributed. Those two are not special to GPU. But then from Dask CUDA, I'm going to import the local CUDA cluster. So here we go. I will do those imports. Now, by default, the local CUDA cluster is going to spawn a number of workers that is equal to the length of the CUDA visible devices environment variable. And since I have 2 GPUs accessible here, that's the number of workers that it's going to want to create. We're also going to assign a client object with our cluster. This is pretty standard practice. The client is basically our runtime interface to the cluster and the Dask scheduler that's running in the background. And you'll notice that I've imposed a timeout here of 60 seconds. This is expanded from the default. That's because sometimes I notice when there's contention on Casper, that cluster object or the client can time out in trying to connect to the cluster. So we're just trying to avoid that. So I'll run this. You notice I have my probing question here of did it work? So that probably implies that no. This preload statement is fine. Don't worry about that. That's just an info. But then here we've got this unable to start CUDA context, and we've got this value error, invalid literal for int with base 10, and then this interesting string. So this is an artifact of running in sort of a PBS environment, which isn't to say that it's exclusive to PBS, but PBS certainly does this. So when you start a job, that job will assign your job to the GPUs that you asked for, and it'll use CUDA visible devices to do that. Now, some systems will set this by device ID, which is an integer, like 0, 1, 2. Whereas PBS will use the GPU's UUIDs, which are these long strings, to assign CUDA visible devices. Obviously, NVIDIA didn't anticipate this or didn't care about it when they wrote Dask CUDA, so it expects ints for this cluster type. So we can fix this fairly easily, but I'll show you how. First off, we're just going to shut down that client because that client is sort of like lingering there in a diminished state. We don't want it to cause problems in the future. So here I'm just going to take a little pause and talk about PyNVML. So this is a collection of Python bindings to the NVIDIA Management Library, or NVML, which this allows users to query, and if you have root access typically, modify GPU characteristics and runtime behavior. So we can import this and use it from Python, but if you've ever used NVIDIA SMI on the command line, it uses the same interface behind the scenes. So we'll do this. Notice you have to init this collection of basically init the interface to the NVML. And then I'm just going to define this loop. So I'm going to loop over the devices I have. You see I get the count. That's just going to be an integer. And then I get a handle for each GPU using this method. Then I can use this one with the handle to get the UUID, and it comes out as a byte string. So we just want to decode this to be UTF-8, so it prints nicely. And then I'm also going to get the compute mode for each GPU using its handle, and I'll explain down here why that's important. But let's run this first. So here we go. We've got our two devices. You can see device 0 and device 1. There's the UUIDs that are currently set. And then the compute mode is default for both of them. And you notice for the compute modes, I have this sort of mapping list here, because otherwise it'll spit out an integer. But if you look at the man pages or the manual for NVML, you can see the mapping there. Okay, so why did I care about the compute mode? I ran into this the other day, actually. So you're likely to run into issues in Python if you're using a GPU that's not using the default compute mode. So there's other ones like exclusive thread and exclusive process. Exclusive process mode, for example, is going to prevent you from using CuPy and a CUDA worker in the same Python process. It basically says you can only create a single CUDA compute context on a single GPU. And for some reason, there was a GPU the other day that was configured to run in exclusive process mode, and this was causing me all sorts of problems trying to run through this notebook. So if you see something like that when you run these commands or you run NVIDIA SMI, make sure that you change. More likely, ask your system administrator to change the compute mode on the GPU, either in Python or using NVIDIA SMI. It has to be the command line version, so you'd run sudo NVIDIA SMI and then change the compute mode to 0, which is default. And you can specify the GPU ID if you want, or if you leave this -i and the UUID off, then it will do it for all the GPUs that it can see. So you want those in default. Otherwise, again, you're going to have problems with not being able to create multiple contexts. So, okay, let's return to the CUDA visible devices issue that prevented us from moving forward. So all this is, again, pretty easy to solve. All you need to do is import OS and then redefine the environment variable CUDA visible devices from the UUIDs to the device ID. So we're just going to change that to be 0, 1. Now, in a PBS job, it's always going to start from 0 because basically your view of it is only the GPUs that you've asked for. So really, you could just set this to be like equal to range of the GPUs that you care about, but here we're just explicitly setting it to 0, 1. So now we'll go ahead again and run the same thing to try to create our local CUDA cluster, and this looks a lot better. Now we've got these two statements. They look concerning because they're in like salmon red here, but basically it's just telling us that it's preloaded our Dask CUDA workers. And we can run client here. And this, if you just run this on the client object, it will give us some nice sort of information about the CUDA cluster, the scheduler, and the workers. See, I've got 2 workers here. And it also provides us a link to the Dask dashboard, which I'll just bring up real briefly here. So this will give you a lot of very useful information for sort of profiling your Dask workflow. Here's the task stream, basically the various tasks as they're running once you tell it to compute. the amount of memory that you're using for each worker on the node. And then if you go to the GPU tab, it has this dashboard for GPU memory and GPU utilization, which is basically going to give the same information that we got in our GPU dashboard. But if we run a Dask cluster that spans nodes, then this will show us information for GPUs across all the nodes, whereas the GPU dashboard is only going to show us information on our particular node. And I'm sorry, I have to move this top bar to get back. There we go. So that dashboard is really useful, and I highly recommend that you sort of have it up on a separate window, and just pay attention to it as you're going through. Okay, so we've done a lot of setup. Let's go back to doing some computation. So now we're ready to scale up. We can use the aquaplanet temperature array that we created earlier, but let's imagine that that's one file, and we need to process 12 of them. Let's say we're moving forward in time. That's obviously not going to fit on a single GPU if we just sort of did a concatenate operation with the CuPy array. But we can construct a Dask array instead on the GPU using the NumPy array that we originally created. So how I'm going to work through this here is I'm going to create a Dask array. It's going to be coming from T, which is our NumPy array on the CPU. And I'm going to define a chunk size here. Even though it says chunks, it's actually chunk size. Of 1,000 elements by 500 elements by 140 elements. So these are sort of the entire time dimension, but then split, the spatial domain's been decomposed into these chunks. So we can go ahead and run that there. And it takes a second to sort of set up the structure. What we're going to do then is we're going to create we're going to map our CPU Dask array to the GPU. So we can do this, we can map all of our blocks or our chunks to be CuPy arrays instead of NumPy arrays. So this is sort of the magic to GPU enabling, if that's a word, enabling our Dask array. And then I'm just going to use this concatenate operation on 12 copies of it to sort of simulate what we would see in terms of size if we were running on 12 files, and I'm using the time axis there. So go ahead. Now, if I print just the object in a notebook, I get this really nice HTML representation of the Dask array. We can see that this would be quite large. It would be over 100 gigabytes. This wouldn't even fit into the node memory that I've allocated. But the chunk size is only 534 megabytes, and we've got 192 chunks. So this is pretty pretty reasonable. Each chunk is pretty reasonable to fit onto the GPU memory. So let's we've already sort of assigned some tasks to set up our structure here. And you'll notice nothing has happened. Remember, it's doing lazy execution, so we have to compute. We're also going to add our mean and conversion to Celsius operation on top of our task graph. So I'll do that there. And then if I run, so I've assigned this to a variable called tg for task graph. So now I have tg.dask. I can show this attribute. And what this will do is this will give us another sort of interactable HTML widget here, which will show us the various steps of our task graph. So it's going to create the NumPy array. It's going to convert it to a CuPy array. We're going to concatenate it all together. We're going to do the means, and we're going to aggregate the result in the end. So this can be a nice heuristic. There's also a sort of a graphing visualization you can do if you have the right packages installed, and that can be useful to look at as well, though I don't show it in here. So so we can see what we're going to do, but we haven't done anything yet because we have not run compute. Nothing's happened over here. So let's go ahead and do that. So if I do tg.compute, this will cause our task graph to go. We can time it, and then we'll store it in this dg means variable. So let's go ahead and do that and see what happens. And hopefully we see both GPUs, really doing stuff here in the GPU utilization. Notice there's a bit of an overhead here, but there we go. Now we've got operations going. We can see that the memory is getting allocated on each of the GPUs. There we go. It's done. It's not, it wasn't like rocket fast, but remember we operated on 12 times the size of the data that we did before. And look at that GPU memory utilization. Because we've defined our chunks to only be a half a gigabyte, we haven't really used too much of that GPU memory on either device. So we could scale this up, a lot further. We could use bigger chunks, for example. That would be another interesting thing to do. And, this would be a case where, again, if we ran this again, I think maybe it would be down to like 12 seconds. There's still going to be a bit of overhead there to set everything up. But we've certainly scaled up our calculations significantly from what we could do on a single GPU in terms of the memory available. So we'll go ahead and we'll delete that so it cleans up. And then I'm going to go ahead and shut down this scheduler. But I guess before I do that, let's just go back to our dashboard. Now we can see the memory usage in here. And more interestingly, if we go to the status, we can see the various operations that ran on each GPU, and we can see sort of maybe where one GPU is waiting for the other to catch up, and maybe do some transfers to concatenate and aggregate that data together to get our result. So we can see how the time was spent in our computation, and it tracks this even though it ran on the GPU. There's nothing special about it running on the GPU in this case. It gives us the same information. So let's go ahead and shut down that client. You see it now frees the memory on my GPU. I'm going to go ahead and close that dashboard since it's no longer live. And we'll just delete, we'll clean up our client and our cluster objects. So now we can move to scheduling GPUs with Dask job queue. So in the above workflow that was all running on a single node, now if we want to span to multiple nodes, we can use a PBS cluster instead of a local CUDA cluster, and basically get the same result. Now here we're going to use PBS to schedule single GPU single task jobs via the scheduler. In some ways, this is an easier setup than the local version. There's less changes we have to make. If we have the following distributed CPU code, you'll see we've imported a PBS cluster, and then we define what each worker job looks like for the PBS cluster, giving it a single core, 35 gigabytes of memory, giving it a resource specification because PBS needs it in its own format. If I submit it to Casper, Casper queue, and then ask for 10 minutes of wall time. And here this says use our high-speed network, our InfiniBand network, which is just a good thing to do for performance. If we want to modify this to instead use GPUs, or in addition use GPUs, I should say, all we have to do is, at least on Casper, is add : and GPUs equals 1 at the end, add an extra bit here, and here, just for fun, I have it specified to use our preview A100s. We have 3 of those on Casper, sort of to prepare for derecho. And these are in the preview queue, and then I'm going to ask for 10 minutes of wall time, and again, use the InfiniBand interface. So here we go, I've defined that. One thing that I always like to do when I'm running a scheduled version of Dask is verify via this cluster.job script that what I put in there looks reasonable. And I can see this looks like a PBS job, and I've got the resource requests that I expect in there. Notice there's a couple of pieces that I didn't specify, like my account. That actually comes from some YAML configuration files that are in my home directory. And if you go in the Dask documentation, it tells you how to set those up, so you don't have to put those in your notebook. And maybe that maybe having your account key in the notebook forces somebody else to change something that maybe don't want to change. So putting settings in logical places is always a good thing to think about when you're setting this up. And then we're going to create our client and point it to this new cluster we've created. And you notice, again, I have a new dashboard for my new cluster. We don't have any workers yet. So one thing with a batch version is it starts off with 0 workers. So we need to scale it. So I'm going to run cluster scale to 2, and I'm going to tell it to wait for the workers to start. Generally, you may not do this, but if you're going to do benchmarking, you probably do want to wait for all of those workers to get going so that you have reproducible results. This sort of, it's sort of a blocking operation waiting for those PBS jobs to start. You'll notice it's returned, so now they have. And if I just run the shell command of qstat on me, I can see I've got my notebook running here, but I've also got these 2 Dask workers which have 10 minutes of time, and they have access to each one has access to an A100 GPU. So now I'm ready to go, and I can, using the same task graph that I created before, I didn't delete that, remember, I can now use this new cluster that I've defined to run the same calculation. Now I'm going to end up running it across the cluster. So this GPU dashboard is not going to show anything. These are my local ones. But if I go over to here Now we can watch this and we can see what's going on behind the scenes of our task stream, and we can see what it's doing. So it's creating the array first. Now it's concatenating those together. It's doing all of the actual like floating point operations in here. Did not take long because we're running on powerful GPUs. And again, if I go to the GPU tab here, I can see my memory usage, and I'm not getting close to the 40 gigabytes that's available on those A100s. So I've basically run the same computation, but now across multiple nodes very easily, I would say. You can see it takes a little bit longer because we're spanning the network, but it's still pretty reasonable for running those operations on 10 files. So now I'm going to go ahead and shut that down. And if I run qstat now, we still have these two Dask workers. That just goes to show there's a tiny bit of delay here, both in PBS's reporting, but also in the time it takes to clean up the jobs. But if you just put like a sleep in there for a little bit and then run it again, it'll reflect that you don't have any, if you wanted to block and wait for your cluster to actually wind down. So just a note about this workflow, it's not currently compatible, at least in the Python API, with the CUDA workers that I talked about earlier. So some of the advanced features that NVIDIA has built into their CUDA workers, like allowing for GPU memory spill onto CPU onto node memory, that's not accessible using the Dask job queue method. However, it may be possible to start up your cluster and workers manually and use CUDA workers. You can do that from the command line and then point it to IP addresses and things like that to set up. It's a bit of a process, especially on multiple nodes. So I didn't want to get too far into it here. But if you try to use, say, the CUDA workers object with the Dask job queue scheduler, it doesn't have the hooks set up currently. Hopefully that's something that they'll get in place. So just some caveats to using Dask on, especially on a GPU. I think hopefully I've shown that Dask is very powerful to use the GPU or with multiple GPUs. But it still takes some setup work, more logically, I think, than code-wise. You have to sort of think through so that your workflow is optimal. And it does incur a little bit of overhead, as we saw when you start computation, especially if you're going across nodes. It's also more challenging to debug a Dask workflow than a serial one. And if you look at the GPUs, setting up Dask is a bit more difficult. The typical task sizes that might work fine on a CPU workflow, they may end up starving the GPU for work, and that overhead is a bigger chunk of time compared to your actual work, and that's not a situation you necessarily want. That's sort of the situation we were in, even in that example. And then worker memory management is more important. I've done a lot of care here to make sure that we haven't exhausted the GPU memory. But if you're not careful and you don't deallocate your arrays reliably, it's very easy to overload the memory on a single GPU. And by default, your flow will fail here. If you have that spill to CPU enabled, it won't fail, but it'll run a lot slower. And then you're not going to be happy either. And the way I look at it is I feel like Dask and GPU offload sort of solve orthogonal problems. If you need a much lower time to solution for like a heavily vectorizable problem, you're probably, a good starting point would be to switch from NumPy and Pandas to CuPy and cuDF. But if you need to scale that up, then that's where you go to Dask and get the bigger problem sizes. And one thing to note, because of limited GPU availability or higher cost, if you're putting together your own cluster or working in the cloud, wait times can be longer as well for V100 GPUs. So, there's just some things to think about in terms of your trade-offs between, empowering your work using these GPUs and also using them wisely, using them, for things that they're fit for purpose, basically. So we have a little bit of time left. I don't know if we'll get through all of this, but I just wanted to sort of introduce cuDF for you, since this will play a big role in, in what Daniel's going to talk about in 2 weeks. So cuDF, it's a data frame object, just like a Pandas data frame. It looks like a spreadsheet essentially. So it's a 2D arrangement of labeled data. I'm going to go ahead and download this data set of Boulder daily weather from PSL in NOAA. And then I'm going to just show how this would look in CPU world using Pandas, if you're not that familiar with Pandas, and then we'll show it in cuDF. So here we go. I import pandas. Remember, this is a high-level collection in Dask too, so this is very apropos to what we just talked about with Dask. And I'm going to use the read CSV method here to read in some data. It's actually not a comma separated variable file. It's a white space separated, so I can use this to use white space as my delimiter. And then I'm going to give it these column names that I extracted out of the file because they weren't necessarily easy to read in the text format that it was in. And for some reason, they use both -998 and -999 for not a number variables. But there we go. We've read it in, and we've done some massaging of the data to get it the way we want. And we can run head to get the top 5 rows. We can see that in 1897, in the beginning of the year, they weren't actually doing any measurements. But if we do a tail, we can see real data from very recently. In terms of like temperature max, temperature min, precip, snow cover. And we can see the memory usage of this. It's not huge. It's 2.81 megabytes, but it's always just good to be cognizant of the sort of memory you're going to use. And I just wanted to point out here that if you do a deep analysis of the data frame, you'll see the true memory usage. Whereas if you don't specify this, it might hide things like mutable objects, like lists and things that could be in your data frame. So we can do complex operations using Pandas, or as we'll see, using cuDF. Very simply in like single one-liners, and that's the power of this. So, let's say I wanted to get the average snowfall for each month in Boulder. I could take my data set, I can filter, I'm going to filter out 1897, so I'm going to make it so that the year has to be greater than 1897, the year column, so we don't have that missing data. Then I'm going to group the entire thing by year and month. So this basically, this is a daily data set. We're basically reducing it down to a monthly data set using this group by operation. And then we take the sum. So we get the sum total of snowfall for the entire month across all days. And then we'll do another group by, we'll group it by month, and that will take all of the years, reduce the years out, and then we'll get like a January through December data set. We'll only look at the snow column. That's all I care about. We could have done that actually back here as well, of course. And then we'll take the mean. So this is a pretty complex operation, ran nice and fast on the CPU. And then we can plot it to get our interesting data. And very simply in a 2-liner, that could have been a 1-liner, we get a nice plot of the average snowfall in Boulder for each month. So that's on the CPU. We can do the same exact thing on the GPU pretty easily. So we would use cuDF to do it. It's part of the Rapids package, as I mentioned before, and it's developed by NVIDIA. So many of the Pandas methods and functions have been replicated in cuDF, though not all of them, just like with CuPy and NumPy. So we'll go ahead and we'll import it. If we go down here, oops, I think this column is supposed to be there. Apologies for that. So we're going to do our read in. You'll notice here, we're sort of doing a drop-in replacement. You notice I've got this read CSV on the same file, with delimiting by white space, but we had to make a couple of modifications. This is because cuDF does have some sort of subtle differences. For example, there's a white space at the start of my file, and because I'm using delim white space, Pandas recognizes I probably don't want that like single white space to be a column in the beginning of each row. cuDF does not, so it'll end up creating a blank column. So here I'm just going to play a little trick and call it X, and then I'm going to drop column X. That's my way of cleaning it up. But I could clean up the data file beforehand, and that would solve the problem too. And then I'm going to use this replace method to replace my null values. The reason is that in cuDF, the NA values method that I used before won't take integers, it requires strings. So instead I can use .replace, and we end up getting the same result. And now this is on the GPU. We're using GPU memory just like before with CuPy. So again, I can run ahead and I can see I've got now the same result. I've got NA values instead of NANDs, that's just the GPU equivalent. And then the memory used is exactly the same, except now that memory is being used on the GPU. So we can run our the same operation as before, but now we're going to run it on the GPU. There is one difference here. I'm running that group by, but I'm actually running it on an index column instead of a data column. And Pandas doesn't care about that distinction. I mean, it cares, but it'll say, okay, I understand what you mean. Whereas QDF actually needs you to be explicit and use this level equals, and that tells it's an index column of month. So in fact, in this case, I would say QDF sort of better adheres to Pandas's own specifications. Pandas allows you to be a little sloppy. But we'll run this. It ran nice and quick on the GPU, but this is just to go to show that you run it on the GPU. Now, if we plot it, we get kind of a bit of abstract art here. And this brings another point, another difference between Pandas and QDF, is that things like group by don't guarantee order of the rows, of the output rows, as Pandas does. So if we want to get the Pandas equivalent, there's a couple ways to do it at different stages. But what we're going to do here is we're going to just sort our resulting series by index. And if we do that for our structure, then we get the same plot that we got before. So that's just another difference to be aware of. And then real briefly, oops, CPU snow is not defined. Maybe I didn't. Oh, I changed it to average snow. Apologies for that. I'll fix that in the version I distribute. So real briefly at the end, let's just show that we do get some benefit from using the GPU here. So we're going to scale up to a bigger data set. Here I'm using the Earth surface temperature data set from Berkeley Earth. So I'm not going to download that because it's fairly big, but I've pre-downloaded it in my copy here. And I give a link for where you can get it on Kaggle, at least for data sets. This is about 0.5 gig. So I'll go ahead and I will read it in. And again, I know some information about my data set. So I understand what I need to do in terms of inferring date times and then which column to parse as dates. And you notice this memory usage for the Pandas version is much bigger. We've got 2.25 gigabytes compared to the file, which is 509. And this is typical of Pandas. It can be anywhere from 5 to 10 times bigger than it would be in disk because it's providing all these nice operations, but you pay a cost. Now, if we move this to the GPU, you can see we're using a similar amount of memory on the GPU. So again, it's something to be aware of in terms of your GPU usage. Now we can compute the global mean August temperature time series using the CPU and GPU. And this is a global temperature data set over a long period of time. So we can look at obviously the warming and the climate. So if I run this on the CPU, and what I'm doing here is I'm saying, give me the month of August, filter after 1900, and then group by the temperature, the average, the date time and the average temperature, and take the mean. So on the CPU, this took 1.26 seconds. On the GPU, this took 12 milliseconds, so a lot faster. And if you were processing like a huge data set, like you might do for a machine learning problem, and you're processing it a lot, that's going to add up very quickly. So this goes to show on bigger data sets the advantage we get of moving to QDF. And if I plot here, remember I'm plotting the GPU version, so we need to convert it to Pandas first. We need to bring the result to the CPU to plot it. That's sort of implied, but here we need to do it explicitly. And I'm going to sort the index, I'm going to sort the series, and then I'm going to plot it. And hey, we can see this looks about right. This looks like our unfortunate recent temperature trend that we're all familiar with. So, that's just a quick little demonstration of the power of Pandas and QDF and the speed up you can get by moving to the GPU for data frames. So we'll go ahead and we'll delete that. These are just some notes about compatibility between the two. I've sort of demonstrated a couple of the differences already, but they're here for reference. Now you notice I didn't talk about X-rays in this session. Partly that was because of simplicity. I think it's simpler just to see things in terms of QPy and QDF. But obviously X-ray is super popular here at NCAR. It's very useful and tightly coupled with like NetCDF data sets and ZAR data. And it is possible to use QPy arrays as the underlying data structure in an X-array structure, in an X-array variable. So you can enable offload to GPUs in that way. There are still some like rough edges in terms of compatibility there, in terms of like access to internal methods from CuPy arrays and stuff like that. But there's certainly efforts that are ongoing to increase that compatibility. And specifically, if you play around with this, and I have a link down here for a quick start on that. But if you play around with this and you run into any features that you need or any sort of issues that you run into, that feedback is greatly appreciated by the maintainers. So I would say see this GitHub repo to provide feedback on that. And maybe in the future we can do a more Xarray focused session on this as well. So I'm right at time. I just wanted to show that there are some resources here at the end for Dask and also high-level collections, and instructions for if you want to run this notebook after the fact and follow and sort of run through what I did and try to replicate it yourself. And here's some instructions to recreate the environment if you're not on our systems. So with that said, thanks for your attention. Really appreciate your time today. We'll continue in 2 weeks with an overview of machine learning in Python and how to use the GPUs to to really enhance that workflow, which is obviously one of the most popular ways to use GPUs these days. I'm happy to stick around for a little while to take any questions that people have. It looks like maybe there were some in the chat that maybe have been addressed already. But if you have a question, you want to raise your hand or just unmute, feel free to go ahead. And yeah, and again, thanks for your time. I'll open up the chat. If you're an Xarray and ML person, please do check out XBadger. Yes, thanks for the pointer. It's sort of the interesting thing about this ecosystem in Python, right? It's why it's so powerful, is that all these packages, not all, but a lot of the packages fit together in sort of a nice a very nice way, and that's why Python is so powerful and extensible.
Thanks for the talk, Brian. This is great. I was curious, the visualization within Jupyter Hub here is pretty nice. Is there anything similar to that if I'm in my own environment where I can visualize a lot of like the GPU utilization and memory, or can I run something and then view it if I'm on the same node within Jupyter Hub? And will it detect that sort of activity?
So, if you're in the Jupyter Hub, then you wouldn't need to install anything into your own environment because it's already in sort of the base environment that runs the Jupyter Hub. If you're instead creating your own install of Jupyter Lab and then doing like an SSH tunnel to it, for example, you can get access to all these dashboards and these visualizations. You just need to make sure that the right packages are installed. And for like the GPU utilization monitor, you'll find some stuff. I'm not sure if it's packaged in with Rapids itself, but it's pretty easy to Google and install into your Conda environment, for example. And the Dask dashboards come with Dask distributed, so you're going to have that by default. So yeah, it's pretty easy to install into your own. And then when you start up your Jupyter server, if you do that manually, you should have access to all these same dashboards in your Jupyter Lab interface.
Okay, cool. Thank you.
Yeah, of course. And you can get visualizations as well from like a Python script. You can get that to output, sort of, you can profile and then save it to an image. But that obviously takes a bit more legwork than just having a dashboard come up where somebody's done all the infrastructure work for you in the behind the scenes.
Exactly. The immediacy here that you provided was really nice. So
yeah. All right. Any other questions or comments? All right, I'm going to go ahead and stop the recording.